So far we've talked about voltage, which makes the electrons move. We've talked about current, which is how fast the electrons are moving once they're hooked up to, let's say, a battery. Now we want to talk about something called the resistance, which prevents the electrons from moving. That's why it's called resistance. It resists the flow of the electrons. Now, the big question is, if I hook up a battery to something and I want to make the electrons move, why do I now want to put something in there which prevents the electrons from moving? Isn't that counterproductive? Well, for one thing, we don't want the electricity to be too much. We don't want the current to be too much, or that could create a fire, could get things to heat up too much, or it could cause some wire to melt, which would be a short circuit, both of which are very unsafe. So for safety, we don't want too much current. So the resistor is going to prevent too much current. The other thing is, the voltage makes the electrons move, and so these electrons are moving. But big deal. I mean, how is that very helpful, moving electrons? So what we want to do is we want to now change this electrical energy into something more useful. So we might take a light bulb, which is going to resist the flow of the electrons, and the light bulb is going to take the energy from the moving electrons and convert it into something more useful like light. A stereo takes the moving electrons' energy and it turns it into something more useful like sound. A fan will take the energy from the moving electron and turning it into something more useful, which is motion. So what we're essentially doing is taking the energy from the electron and converting it into something more beneficial. Symbol for the resistance is letter R. That makes sense. The unit, though, is the ohm, and we abbreviate ohm with the Greek letter O, which is omega. We don't want to abbreviate ohm with the letter O, because that looks like we just forgot the units and have an extra zero on the end. So if my resistance is 10 ohms, and I write 10 O, looks like I wrote 100 and forgot the units. So we use the Greek letter O, which is omega, and that then represents our 10 ohms. Now the way that these things are related, voltage, current, and resistance, is through Ohm's law. So Ohm's law says that the voltage is equal to the current times the resistance. So if I have the same resistance and I increase the voltage, that means I increase the current as well. If I have the same resistance and I decrease the voltage, I decrease the current as well. These objects that keep the same amount of resistance are called ohmic materials. An example of an ohmic material would be a resistor. And for an ohmic material, if we graph the voltage versus the current, we see that the resistance is the ratio of the two, rearranging Ohm's law, voltage over current. And so if the resistance doesn't change, and the resistance we can see here is the rise over the run of the graph, that's the slope. If the resistance doesn't change, the slope doesn't change either. And so it's a linear relationship. This is an ohmic material. However, there are certain things called non-ohmic materials. This means that as we increase the current, the resistance changes. In other words, the slope changes. And so for non-ohmic materials, it's not a linear relationship. As we change the current, the resistance changes as well. So we have two ohmic materials, constant resistance, and non-ohmic materials, variable resistance. An example of a non-ohmic material would be a diode. This is like a device that is like a one-way street. It only lets the current move one direction through the device. Now, not only do these light bulbs and fans and speakers have resistance, the wires have resistance as well. But the wires don't do anything. So although they're taking energy from the electron, they're only warming up the wire. It's wasted energy. So we want to look at what affects the resistance of the wire and how to reduce that resistance so we don't waste or lose any energy to the wire. The one thing that affects the resistance is the length of the wire itself. The longer the wire, the more the resistance. The shorter the wire, the less the resistance. Think of an analogy this way. Let's say you're driving from New York to Philadelphia. You encounter pretty much resistance because of the cars in your way. However, if you drive from New York to Miami in Florida, you'll encounter a lot more resistance because there's a lot more road to cover. So having cars get in the way is your resistance. That's the analogy. Driving a longer distance, there'll be more cars that you encounter. Another thing that affects the resistance of the wire is the cross-sectional area. That's the width of the wire. So the wider the wire, the less the resistance. The shorter the wire, the more the resistance. Think of this analogy with cars again. Let's say you're driving down a one-lane highway. There's no way to get around the car in front of you. And so you encounter a lot of resistance. That would be your narrow wire. However, if you drive on a 4-lane highway, then you can go around the other cars and there's less resistance. This would be an example of our wider wire. The next thing that affects the resistance of the wire is the material itself. Metals are good conductors, so they have a low resistance. Insulators have a high resistance because they don't conduct electricity. To continue with our example of cars, if we drive over a stone road, that's going to be a lot more resistance than if we drive over a macadam road. So the material we drive on affects the resistance, and so the material the wire is made out of affects resistance as well. The last thing is temperature. With temperature, the colder the temperature, the lower the resistance. The hotter the temperature, the higher the resistance. And the reason is because of the entropy of the material itself. Entropy is just saying how organized or how orderly the particles are. So as we get colder, the particles get more organized, which means it's easier for the electrons to move from one atom to another. And therefore there is less resistance. Now for certain materials though, if we get to a cold enough temperature, the resistance continues to go down and go down and go down. And for certain elements, for certain materials like gold, at a certain temperature the resistance goes to 0. And we refer to these as a superconductor. So a superconductor has 0 resistance at or below a certain temperature. What this means is that if we connect a battery to a wire and we get the current moving, if this wire is made out of gold and we get it below that critical temperature, even if we remove the battery, the current will continue to flow. So the current will continue even if the voltage was removed for a superconductor. Now the best explanation I've ever seen that explains what a superconductor is doing is it's more of a siphoning effect, that as the electron is moving it creates a vacuum which kind of drags or pulls the other electrons with it. And the reason that superconductors are so important is because if we can get a superconductor that works at room temperature, so if the critical temperature is room temperature, that means none of the energy is lost to the wire itself. This is important when we send our electricity down our power lines. They have to move for miles, and so a lot of electricity is wasted as we transport electricity down these power lines. But if we can get a superconductor to work at outside air temperatures, then none of that energy is lost and everything is more efficient and we save money. Right now though, the best superconductors that are out there only exhibit superconductivity at or below temperatures of about 150 Kelvin, which is still about 120 degrees Celsius below 0. So again, that's one of these cutting edge areas of science that we're looking to material science and how to get better superconductors. So again, we have voltage, which makes the electrons move, current is how fast the electrons are moving, and resistance prevents the electrons from moving. It takes that energy from the moving electrons and turns it into something more beneficial like light, sound, or motion.